Okay. As soon as I pull up the announcement slide, everybody clues to the big yellow box that says there's no class on Friday. Oh, okay.
Nice.
Hey, thank you.
What, you don't like being in class?
No, I have, it's a very important family day for me, October 14th, now that you don't have class. So, you know,
Okay.
I'd love to invite you, but you're not gonna be here, so.
Okay. I'm not going to be here. I'm going to be out of town. So here's what we're going to do. That lecture. So today we're going to talk about shear moment diagrams. We're going to talk about shear moment diagrams on Friday or on Wednesday. But on that sort of ends that topic. Friday, the only thing that I'm discussing in that video is deflections for beams, but just the background. So it's the same process. We're still using virtual work, but there's some slight tweaks to it. The two main, or I guess three main tweaks are that instead of EA, it's EI. And you know, we have, that's the first tweak. The second tweak is that instead of little f, big F, it's little m, big M, and that we have to integrate them. And then the third tweak is the inclusion of unit conversion factors. And so all I'm doing in that video is just sort of setting the stage. We don't have any examples that we're going through in that video. So if there's any one video to sort of watch on your own time, it's the perfect one. So I actually already recorded it. I'll post it to the playlist after Wednesday's lecture. And I'm going to count everybody present that day on the attendance because, you know, I mean, we're not having class, so that's not on you. So I'll just count everybody here. But don't forget that your project 1 submittal is due Friday. So Wednesday, we'll probably take a little bit of time, see if anybody has any questions about it. Okay, so as for updates in here, attendance grades are up to date. All the homework grades are up to date. Homework 5.5 is due today. Homework 5.6 is assigned today, and it's due Wednesday. I'm going to assign homework 5.7, but it's not going to be due until Monday because you've got your project submittal due on Friday. I really don't like having two things due at the same time. I try and avoid that as much as humanly possible. Sound good? Okay. Let's talk about shear and moment diagrams. Now, the topic of discussion today is, or at least the focus of our example, is shear and moment diagrams for beams with internal hinges. But there's something we kind of glossed over, and I kind of want to take a second and talk about that, and that's internal indeterminacy, right? Remember those little I formulas, the IE and the IT? We didn't talk about that for beams and frames. And now that we're discussing internal hinges, it's a perfect day to talk about it. So I want to talk about internal indeterminacy in beams and frames. And there's an interesting little finding that happens. Notice how I have a formula for IF, but I don't have something listed for IB, the internal indeterminacy for beams. But you're going to see what happens. It's kind of nifty with IB. Okay, so let's just make sure we're all on the same page, though. Again, back in the land of shear and moment, we're still using our same relationships for we're still using our relationships for between load and shear and moment to develop these conclusions that we use for our graphical approach. Same process, same procedure. But now let's go back to this. Okay, so let's recall stability and determinacy. Okay, now we had derived some equations for IE and IT. Okay, so here was our formula for IE, and I'm actually going to write this on the board. This one, because this one's kind of nifty. R minus EC plus 3. Okay, now where did this formula come from? Okay. Remember, this formula was basically comparing the number of unknowns to the number of knowns, right? R being the number of unknown support reactions, and EC plus 3 being the total number of known conditions on the structure. We know 3 of them from our 3 equations of equilibrium, the sum of forces in the x direction, sum of forces in the y, and sum of moments. But we also know any conditional equations based on whether or not there are hinges in the structure, right? So we were able to compute the external indeterminacy pretty easily. Now, we had some conditions on that. You know, the reactions can't all be concurrent, they can't all be parallel. But, I mean, you know, that being said, I think this was pretty straightforward. Now, for trusses, we had an internal indeterminacy. And the internal indeterminacy was the same. The number of unknowns minus the number of knowns. What was the number of unknowns? What was the number of support reactions? And the total number of members. Now, a more apt way of writing that formula would be 1 m plus r minus 2j. Why 1 m plus r? Because for every member, there's one unknown. In trust land, each member only contains an axial force. Okay? So m plus r and then minus 2j. Why was it 2j? Well, because for joints are concurrent force systems. Each joint must satisfy 2 equations of equilibrium. Okay. I'm doing that thing I don't like professors do where they write all over the place. So we'll just keep everything over here. Okay. And keep in mind, trust has to be externally stable, has to be constrained against rigid body movements, so on and so forth. Okay, now let's talk about what happens for beams and frames. Now, first off, we haven't really talked about what fully defines a frame or what the difference between a frame and a truss is, but I would argue that a frame is basically everything a truss isn't. So, for example, with trusses, we say all the loads are applied at the joint. We don't say that for frames. You can put loads on the joints, on the members, put them anywhere. For trusses, the members are connected with frictionless pins. For frames, not. Rigid connections. Centroids have to be aligned for trusses, not necessarily for frames. So what that means is that if I look at the number of unknowns inside the, so if we try and develop a formula for the internal indeterminacy in the frame, we say unknowns minus knowns. So our number of unknowns becomes the number of reactions plus 3m, not 1m. Because for frames, each member has 3 possible unknown components: an unknown axial load, an unknown shear, and an unknown moment. We didn't need to worry about shears and moments in the land of trusses because of the assumptions that we bake into truss analysis. Shears and moments don't exist in truss members. Now, excuse me. Now, as for the number of knowns, I'm going to say that for every joint, we have 3 equations of equilibrium plus any equations of condition. And so that is my formula for IF. Very plug and chug, no more difficult than anything we've done before. But something really cool happens when we look at a beam. Beams are just frames that are horizontal members. They're just horizontal. Okay? So one way of looking at a beam could be like this. 1 member, 2 joints. One way could be like this. 4 members, 5 joints. I don't care how you shake it. For beams, that's always going to be the case. If you got 6 members, you got 7 joints. If you have 83 members, you have 84 joints. It's always just linear, okay? So what happens is this. Watch what happens when we plug this in right here. So we have, let's do some algebra. So, watch this. IF equals R plus 3M minus 3J plus EC. Let's just use the simple case because I'm kind of lazy. M equals 1, J equals 2. Okay. Watch what happens. Okay. 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 For beams, what ends up happening is that the internal indeterminacy ends up equaling IE. And this would work if I used 1 and 2, or 4 and 5, or M and M plus 1. It wouldn't matter. Okay? So there are 4 formulas for indeterminacy, but really 2 of them are the same. So we have the external indeterminacy, then we have internal indeterminacy for truss beams and frames, but the internal indeterminacy for beams equals external indeterminacy. So, does that make sense? And again, we could go through the algebra for general cases and we find the same story. In fact, your FE reference manual actually only lists IT and IF. So, because you could make the argument that this and IE are kind of the same too. So, does that make sense? Good. I like that. Any questions? All right. Now let's get into the land of internal hinges. One question we haven't dealt with is how to draw the shear and moment diagram for a beam with an internal hinge. Or how about another way of asking it? How does an internal hinge affect the construction of a shear and moment diagram? The short answer, it doesn't. Here's the longer answer. Whenever you have an internal hinge in a beam, you use that internal equation of condition to solve for the reactions. So those reactions are the magic values necessary not just to satisfy the equations of equilibrium, but also the fact that the sum of the moments at the hinge is equal. Sum of the moments at the hinge is equal to 0. So once you find those reactions, they already meet the requirements of the hinge, and then from then on you can kind of ignore that hinge. It doesn't exist anymore. You draw the shear and moment diagram the same way, but that hinge stops mattering. And I really want to go through an example on this because I can't tell you how many times on homeworks and exams I've seen situations where there's an internal hinge and students are trying to change the shear and moment diagram at the hinge, but you should sort of just ignore it, okay? And the best way of going through that is to go through an example. So this is what we're going to do today. Let me see, there we go, okay. All right, so here's my example. I copy and pasted the image again here. I'm going to use that as my little cheat. Here's the beam, and I want to draw the shear and moment diagram for this beam, okay? Now, I've got a hinge right here, okay? Now, before we get into this, let's make sure that we're all paying attention to the fact that I'm going to have a vertical reaction right here, a vertical reaction right here, a moment reaction right there, and then a horizontal reaction right here, but I think we all know what that horizontal reaction is. Notice I didn't give you the reactions for this problem. We need to develop that relationship with the reactions in this problem to understand what's going on. So, you tell me, how do I find the reactions? What do I do? Okay, so if I sum, okay, let's do that. All right, but let's not write anything down just yet. Let's do that. So if I sum moments at A, I don't have to consider AX. I don't have to consider AY, but I do have to consider this. So I'm going to have MA plus whatever moment contribution comes from this, plus the moment reaction at B, or plus the moment generated from the reaction at B equals 0. So if I sum moments, I'm going to have two unknowns in that expression, MA and BY. We can do that, but it's not going to give us an answer, right? Neither will summing forces in the Y direction. Because if I sum forces in the Y direction, I'm going to get AY going up plus BY going up equals whatever the heck all this is going down. Whenever you see an internal hinge, what action should that trigger in your head? What do you do?
Slice.
Cutting a section with the samurai sword or the lightsaber if you happen to be a sci-fi fan. I want to slice through this grid or this beam right here. Now we are going to sum moments at A, but not now, okay? And I'll show you why here in a second. Now if I cut a section right there, which direction do you think we should look? Left or right?
Right.
Right. So let's cut a section and look to the right. So we've got and this is 3 kips per foot. Now let's make sure everybody's paying attention this morning. What is that dimension right there? 20 feet. It's not X. That's the critical point. We are cutting a section through a particular point in the structure. So I wanted to make sure that this was held separate from what we did on that last homework, right? Because that last homework, or the one with Excel, we were trying to derive a function for shear, a function for moment. We're not really worried about that right here because we're trying to find the moments at a particular point, okay? So this is 20 feet. Now, we have an unknown shear and an unknown moment. Just to make sure we're all paying attention, the shear, which direction do I draw that for positive shear? Say it again? No, for shear. Yeah, shear, positive shear, if I cut a section and look to the right. No, it's up, right? So if you cut a section, through a beam, and you split it apart, shears are downward positive on the left, upward positive on the right, okay? Moments are positive like this, positive like that. So positive moment goes like this, okay? That's one of those things you just kind of have to remember. So V and M. But what do I know about this M? It's 0, and the only reason I can say that is because I cut through a hinge. So I'm going to write that. I'm going to say M equals 0. That 0 looks like a weird 6. Okay? Now, distributed load, collapse that into a concentrated load, and how much is that?
60.
60. And from our cut, 10 feet. There we go. Now we're getting somewhere. So now I'm going to sum moments at the hinge. And maybe what I'll do to be consistent, to say I'm summing moments at the hinge looking to the right, equals 0. And so I have 60 times 10 going this way, by times 20 going this way. Oh, I'm getting clairvoyant. So 600 foot kips equals by times 20, so therefore by is positive 30 kips, which is 30 kips up. Oh, wait, we need the Windows is being all sorts of. So I wanted to sort of break that off of my notes and say this is a separate structural analysis of just that section cut. Now I could solve for the internal shear. You know what? Why don't we just do that just for the heck of it, okay? We are not going to need this internal shear right here at all for the analysis, but let's just do it for the heck of it. Alright, so V is going up, BY is going up, which is 30 kips, 60 kips is going down. We do not need that in any way, shape, or form. So why did you do it? You'll see. Trust me. Just trust me. Every now and then I've got good ideas. It's very rare. Okay. With me so far? Okay, now let's go back to the original structure. Okay? So alright, so I'm going to cheat a little bit. Whatever. Goodness gracious. Windows does not like me today. Okay, so now let's go back to the original structure. And remember, we had Windows. We had AY, we had BY, we had AX, but we know that's 0, and we had MA. Now, what makes this different this time is now I know what BY is. BY is 30 kips. Now your suggestion of summing moments at A, we could have done that earlier, and there was absolutely nothing wrong with that. The only thing is we would have gotten an equation that wouldn't give us an answer for one solution. And so I think we'll see that right now. But there's nothing to say we couldn't have done it.
So we have solved or gotten an equation in terms of AY and BY, doing that, and then also use the forces in the Y and then solve the two equations at once?
Not necessarily, because, okay, I see what you're saying. That wouldn't have worked because summing forces in the Y would give us AY and BY's unknowns. summing moments at A would give us
Oh,
MA
right,
and
okay,
BY as
so
unknowns.
right.
So we wouldn't have had the same unknowns. Does that make sense?
Yeah, but I could choose a different point in theory, right?
Yeah, but it still wouldn't matter. Well, okay, so let's say some moments at B. You'd have A, Y, and MA as unknowns. Like it wouldn't,
What about the hinge?
well, that's what we just did.
Can you do it without cutting a section and solve them?
No. Because, and the reason why is because the equations of condition, like the hinge is telling us that the sum of the internal moments is 0.
Right, okay.
So that's why you have to cut the section. Now, we could have cut the section and looked to the left. That would have just been, it would have, what would have happened if we cut a section and looked to the left is it would have made our algebra infinitely more complicated, but we would have got the same answer. Does that make sense? Okay. Now, let's go back to this structure. So I have a 3 kip per foot distributed load over a distance of 50, 60, 20, 80 feet. So 3 kips per foot over a distance of 80 feet is how much? 240. And from A, how far is that?
40.
Say it again. 40. So that's going to be about right there. 240 kips. And from A, 40 feet. So now let's sum moments at A. Do I consider AX? Matter if I needed to, it's 0, right? But no, I don't, because it's going right through A. Do I consider AY? It's going right through A. What about MA? Yes. Which side of the table does it go on?
Right side.
Right side. Do I multiply it by a distance? No, because it is a moment. So, likewise, if this beam just had some, 60-foot kip moment right there, I would not multiply it by a distance. I would just add 60. All right. Does the 240 kips generate moment? Yes. Which side of the table? Left side and the moment arm? All right. The 90 kips generates moment, and what's the moment arm there? It's 40 feet. And now what about the BY?
It's the other side.
Exactly. So it goes on the other side, and it's a moment arm of 80 feet, right? Now, the reason why we waited until now is because now we know what BY is. If we hadn't cut our section first, we would have just had MA and BY, we wouldn't have had anything. So it would have been a little frustrating. Okay, so let's see what we can figure out here. So 240 times 40, that's 9,600. 90 times 50 is 4,500. So that's what, 14,100. Equals MA plus 30 times 80. So MA is positive, what is that, 11.7?
Yep.
Did I do that right, 11.7? And that is that way. I'm just curious, does anybody see something on the structure that we ignored just now? Didn't even talk about when we sum moments. The hinge. We didn't even talk about it. We didn't even think about it. From here on out, you can take that hinge and just toss it out of your head. It doesn't exist. It's done. Don't have to worry about it. We've already utilized our equation of condition. We're already taking that into account. Nothing matters anymore with that hinge. All right, so tell me what to do. You tell me. What's left for the reactions? Some forces in the y direction. Let's go ahead and do that. So what do we got going up? We got AY, we got BY, but we know what that is. We got 240 and 90, not 30, 90. Going down. Let me get my other beam here out of the way. $240 and 90 is 330. What do we think? So far so good? And again, what did I just kind of ignore this whole time? The hinge. I want to train you. That hinge, stop thinking about it. Doesn't matter anymore. All right, is everybody okay on the reaction side? All right, so watch this. So now we have the beam. Now let's draw shear and moment diagrams for the beam. And you're going to see something really cool happen here. Now, remind me, this is 30 kips. This, 300 kips. This, 700 foot kips. Okay. This is cool stuff. And again, what are we going to ignore like it doesn't exist? The hinge. When we're constructing these things, we are going to ignore it. We're constructing these diagrams, we're going to ignore that hinge. Okay. Start off with the shear diagram. So I start at 0. What's the first thing I do? Say it again. Up by that reaction to 300. Now what happens, let's come up with some letters here so that we're all speaking the same language. So that's A and B, we'll call that C. So D is our hinge. Letter D is our hinge. Again, we're not gonna pay attention to it when we're constructing our diagram, but just so that it's there. What happens from A to C? I drop down, don't I? How much do I drop down? What's the total amount? 150. So if I'm at 300 and I drop down 150, that puts me at 150, and that path is linear, right? So that's about the best straight line you're getting out of me. So I'm at 150. Now what do? Drop down again. 90 to put me at 60. That's going to get a little crowded. Let me see if I can do a little better with that. Bear with me. Let's jump up here. That's 150. then drop down to 60. Now, again, that hinge does not exist, okay? So if I am at C to B, how much distributed load is from here to here? 30, so 3 kips per foot, that's 90, right? So if I'm at 60 and I drop down 90, what's that put me at over here? Negative 30. So and then that reaction brings me back up to 0. I'm curious. Let's look at something. What is this value right here? Well, I was at 60. How much load is in right here? How much load is this right here? 3 kips per foot over a distance of 10 feet is 30. So if I'm at 60, I drop down 30. That puts me at what, 30? When we cut the section at the hinge, what was the shear value in the hinge that I said we weren't going to use but would be nifty later? 30. Well, by golly gosh, gee, the shear diagram is 30 at the hinge. The geometry gods have also smiled down on us because in order to determine these areas, I have to find this point right here. But this is 30, this is minus 30, so what's this distance? 10. So let's get some areas. Now, do you remember how the little trick I taught you to find the area of a trapezoid? Of this big region right here? How do you find the area? You average these two times the length. So what's the average of these two times the length? It's a lot. It's going to be a big one.
11,250.
11,250. Do I have a second on that? What about this region right here? This second region from C to D. I am going to actually compute these areas separately, but what about this region? 450? All right, what about these triangles? They're going to be the same, they're just going to be opposite sides. So 150, so this is going to be plus 150. Minus 150. What is the sum of those areas? Oh, we're doing great.
Probably 11,700.
What's that?
12,000.
Well, hold on. These are going to cancel each other out. Plus
yeah,
150
yeah,
and minus 150. So really, it's just these two.
Yeah, so that's 11,700.
11,700. Have we seen that moment show up before?
That's our reaction.
That's our reaction. That's our moment reaction. So in order for our moment diagram to start at 0 and end at 0, what that moment reaction is going to do is cause a sudden jump down, right? So let's draw the moment diagram. Let's draw it. So we start at 0, big jump down. To 11,700. All right, so what happens from here to here? From A to this point here, C. We jump up, right? So if I'm at negative 11,700 and I jump up a positive 11,250, what's that put me at? Negative 450. So I'm going to be at negative 450 right here. Now, is it going to go path 1 or path 2? Path 1, right? Lot to a little, right? So now my parabola is going to look a little disjointed, but that's okay. What happens from here to here? If I'm at negative 450, where do I go here? 0. Interesting. And again, lot to a little. And then what do? Little to a lot. Or sorry, a lot to a little to 150, little to a lot, back to 0. But look what happened. You got a 0 right here. By golly gosh gee. Wasn't the internal moment at the hinge 0? There's a check for you. Craziness, isn't it? I love structural analysis for stuff like this. It just sort of checks itself. It has a tendency to not reconcile. That was so dumb.
I got that.
That was so dumb. I'm such a dork. I know.
That's the sign. That's the sign that's in the rack everywhere. Check yourself before you.
I'm a dork, I know, it's okay. So, again though, like, when you cut a section, remember the very first shear moment homework we did, like homework 5.1, when all I wanted you to do was cut sections and get internal moments, internal shears. All those were the values on the shear diagram, the values on the moment diagram. So when we cut a section at the hinge, we got shear was 30, moment is 0. That better be reflected on the shear and moment diagram. Once you solve for the reactions, that hinge, it doesn't exist. I mean, you can use it as a point of reference when you're constructing your shear and moment diagram, but it doesn't matter anymore, okay? What do you think? It's not too bad, right? Other than one topic, I don't have really anything else to talk about when it comes to shear and moment diagrams. That one topic is frames. How to draw shear and moment diagrams for frames. And the only difference is taking this and doing it like that. It's not hard. It's just that. It's just rotating. What we're going to do after that is go into the land of deflections for beams and frames. And what we're going to find is that with trusses, we had this, right? When we sum these up, for beams, we're going to have this, but unfortunately, we're going to have to integrate it. And the reason that we're going to have to integrate it is because I don't know about you, but the moment diagram seems to go up and down, up and down, up and down. It's not constant. But fortunately, the integrals are very simple. Integrals that your Casio FX115 ES Plus or similar scientific calculator should just do on its own. Makes your life a lot easier. The hard part is actually writing the functions, not the integrals. The integrals is the easy part. I'm going to give you an extra 5 minutes of your life back. That's all I've got, everybody. I will see you all on Wednesday.